Hey guys, welcome back to Explore Electronics. This video is all about Module 1 video lecture of Embedded System Design subject, that is BEC601 of 6th semester. So let us get in and see complete Module 1 and what are all the concepts there and which are all very important for exam as well. Let us get in. If you look at the syllabus of Embedded System, this is BEC601, and starting from what is Embedded System, we will be going through the classification, history, and application areas, and also what is the purpose of embedded system. And there are some differences here, like microprocessor, microcontrollers are the main parts of embedded system. We need to understand the differences and differences between the type of controllers, that is RISC and CISC, and the type of architectures like Harvard, VonNeumann, and controller architectures, and Big-endian, Little-endian style of writing the data into the processor, and memory subsystems. Then sensors and actuators were connected with the processors to process the data. Then I/O subsystems like LEDs, 7-segment display, and relay, optocoupler. So these are very much important in embedded system to drive the data and also to take out the data. So finally, external communication interface and embedded firmware, which is required as a software to work on, and some other system components. So here you can refer the first textbook for this particular module, Shibu KV Introduction to Embedded System. So let us get in and see all the concepts from what is embedded system till other system components in this module in one go. Let us get in. So these are the topics from module 1. So first of all, what is embedded system? Embedded system is a electromechanical device or electromechanical system which is designed to perform specific application or specific function. And it will be consisting of hardware as well as firmware. We call it as software. So this embedded system definition is very important. So this carries 1 marks if the question is asked on embedded system diagram, and also they may ask to define the embedded system. So it is basically a electromechanical device. Why? Because it will be consisting of electronic hardware and also firmware with some mechanical system with that. Examples are electronic toys and mobile handsets, washing machines, air conditioners, automotive control units, set-top box, what we see, and DVD or CD players. So all these are specific functional devices. Means electronic toys, if you see, those toys will be performing only certain operation. That is not a general purpose system. That is a major thing we need to understand in embedded systems. And also mobile handsets, which are there previously, not the smartphones. Mobile handsets in the sense the keypad phone what we have used previously before the smartphone comes into existence. So these things will perform only certain operations. Similarly, washing machine, AC, all these are examples for embedded systems. So embedded systems are unique in character and behavior. They will do certain operation and they will be having specialized hardware and software required to perform that operation. That is what embedded system is. Now we need to understand the difference between what is a general purpose system and what is embedded system. So the general purpose system, in the sense, it will be like a computer. It will do whatever the functionality we can get out of it. But embedded system is one, after the assembly is done, it will perform only certain or particular operation, right? So let us see the difference. The very first difference is that system which combination of generic hardware, means general hardware, and generic purpose operating system. And it will execute variety of applications. Here you can see the difference. But embedded system is a combination of specialized purpose hardware and embedded OS for executing specific set of application. This is the major difference you need to understand. Variety of applications general purpose system can do, specific set of applications embedded system will do. The second thing is with respect to OS is concerned. Here general purpose system contain general purpose OS like GPOS we call, but embedded system may contain OS or may not contain OS. Sometimes it will be having a embedded OS inside, otherwise there will be no OS at all. But in the general purpose system, if you see CPU, that requires a OS, correct? Then comes the third difference. The applications here in the general purpose system are alterable. You can use a general purpose system for doing any other application depending on the programming. So this is programmable. So the embedded system is one-time programmable. It can't be reprogrammed. You can see here the firmware of the embedded system is pre-programmed, means once we program it, and not alterable. It is not able to alter it again once it went to the user end system. And the fourth difference is performance is the key deciding factor here on selection of the system. Faster is better. We will be choosing the processors which are very faster in operation, right? That's why general purpose system is, we will be deciding on that depending on the how fast the system is, how good the performance is. But in the embedded system, it is application specific. It should perform that application correctly. Means the power requirement, memory usage and performance are the deciding factors, and they need to perform depending on the application what we use over here. These three are the deciding factors. So then we can see more differences here. The fifth difference is that less are not tailored towards reducing operating power requirements. Here the power requirement is not so critical, since we will be applying for different applications. Sometimes it may consume less power, sometimes in applications it may consume more power. But here in the embedded system, we will be operating most of the time with the batteries or with some standard volts. That's why it is highly tailored to take advantage of power saving modes. There are some power saving modes as well in the embedded system. And sixth point is that response requirements are not so time critical. Response requirement in the sense, as soon as we give the input, we are not expecting the output. It takes some time to process it. But in the embedded system, like mission critical systems, the response time is very much critical. There will be a specific time limit, so that as soon as we give the input, we are expecting the output in that critical time unit. So response is critical. Then comes the seventh point here. It need not be deterministic in execution behavior. Means we can't deterministic in how actually the system is executing here. But execution behavior is deterministic. It means we know how actually it should behave. We will be having some hard real-time systems as well, as that is what highly critical time we say. These are the differences between general purpose system and embedded system. In the exam point of view, this is very important question. You may get this question for 5 to 6 marks. You need to remember at least 5 to 6 differences. Then comes the history of embedded systems. What is the history of embedded systems? First recognized modern embedded system is Apollo Guidance Computer, that we call it as AGC. First mass produced embedded system is D17, that is Guidance Computer, Autonetics. So this is just for your information. You can just go through the history of embedded system, how it is evolved, what is the first thing comes into existence, how the systems which are there nowadays. So to know that, just we can understand a classification, and also we will be having based on the generation as well. That helps you to understand the history. So then comes the classification. This is also very important. Based on the generation, you can classify based on the complexity and performance requirement, based on the behavior, based on the triggering. The very first thing in that is based on the generation. We categorize embedded systems as first gen, second gen, third gen, fourth gen, like that. What is first generation then? The only difference what we are going to make out here is the early embedded system builds on 8-bit microprocessors like 8085, Z80 and 4-bit microcontrollers. Remember these 2 points, 8-bit microprocessors and 4-bit microcontrollers. Digital telephone keypads and hardware, simple hardware it will be consisting of. So remember 8-bit microprocessor, 4-bit microcontroller. Second generation. So this 8-bit capability increased to 16-bit microprocessors now, 8 or 16-bit microcontrollers now. So 8-bit, 4-bit increased to 16-bit and 8-bit here with respect to mu-P and mu-C. Here bit complex systems are came into existence. So first generation microprocessors and controllers are used over here. So SCADA system is an example for a second generation system. So if you see the third generation system, then it will be increased to 32-bit capability. So the processor capability increased to, it will process 32-bit at a time. Here it is increased to 16-bit at a time. Initially it will be at 8-bit at a time. Means 8-bit information it will take. There are 8-bit of information it will take and process. So it is increased to 16-bit in second generation. It is increased to 32-bit in third generation. Similarly, if you see fourth generation, it might be increased from 32 to 64, or there might be some more complex systems in 32-bit itself. In the third generation, DSP processors are comes into existence. Robotics and media is an example for this. In fourth generation, SoC, that is system on chip. In a single chip, you will be having multiple chips inside. So we call it as system on chip. So complete system will be there in a single chip. It is reconfigurable processors and multi-core processors comes into existence in fourth generation. So the examples are smartphones. It is very complex and powerful. So that is all about the classification based on the generation. Now we can classify based on the complexity and performance requirement as well. Like small scale, like a toy, electronic toy is an example. Here we will be using a very simple or not time critical performance device. It will be only operate on 8-bit or 16-bit microprocessor, microcontroller. The very best example is a toy here. It will do certain applications what we provide. And OS is not at all required in toys. Then comes medium scale. Medium scale in the sense hardware, firmware requirement will be there here. It is slightly complex compared to small scale. And built on medium performance, low cost means 16-bit or 32-bit microprocessors. Usually it contains an embedded operating system. It can be a general purpose system if it is bit complex, but it will be generally having embedded operating system in it. And industrial machines are example for medium scale. Then comes large scale or complex embedded systems. Here 32-bit or 64-bit processors are required here, since it will operate a bit faster and it is bit complex firmware and hardware it is consisting of. Maybe consisting of multi-core processors. Multi-core processor in the sense a single processor will be consisting of internal 2 to 3 processors like that. And it will be having a high performance critical systems, like in army we will be using some missile critical systems. They will be triggered on time like that, and it will be expecting a high performance. And also decoding, encoding of media, some cryptographic functions to provide a high security devices like that comes under large scale or complex. So 3 types depending on the complexity and performance: small scale, medium scale and large scale. Then comes classification based on deterministic behavior. Deterministic behavior in the sense here the time critical or the task execution behavior will be determined or non-determined like that, which will be having a high critical time or it will be not. So this classification applicable for real-time systems. It will be operating in a real time. When something is triggered, when something is happened, it should respond immediately in such cases. So task execution behavior of this system will be a deterministic or non-deterministic. Based on the execution behavior, real-time embedded systems are divided into hard system or soft system. And then the next thing is depending on the based on the triggering. Embedded system which are reactive in nature will be based on the triggering mechanism. Means there will be an event triggered or time triggered. Means we will be fixing a timeline for that. After 30 seconds, this event should be triggered. It is like you will be having a tank filling mechanism, automated tank filling mechanism. Whenever it fills to the 90% of the tank, it should be triggered and turn off a switch, right? That is how it is. So those things will be event triggered or time triggered systems. We can categorize as triggering mechanism as well. Then we need to understand what are the application areas where we will be using embedded system then. In consumer electronics like camcorders, cameras, we will be using embedded system. Household applications like TVs, DVD players and washing machines, fridge, microwave oven. These are the applications of embedded system. Nowadays TVs become smart televisions. They will be having a processor inside. There will be some real time. They are not categorized under embedded system. The earlier TVs, even if it is smart TV, we can consider it as a embedded system. Then home applications like automation and security systems like AC, sprinklers, intruder detection systems, cameras, again fire alarms, everything which you are using in a day-to-day life, which is not so application generalized, it will be for a particular application, you can say it is a embedded system. Similarly, in automotive industry like ABS, anti-lock braking systems to provide more security to the braking of the automobile. Similarly, engine control, ignition systems, navigation systems are examples. In the telecom sector, cellular phones, the earlier cellular phones what I said. Similarly, telephone switches, handset media applications. In computer peripherals like printers, scanners, they will do certain functionality only. They are not generalized, right? Fax machines. Similarly, in computer networking, routers we see, switches, hubs, and firewalls. In healthcare, we will be having some scanners, ECG machines, EEG machines like that. Measurement and instrumentation will be having multimeters in digital CROs you may have seen in your labs, logic analyzers like that. And also in banking systems, what are all the ATMs we see? All those are embedded systems. Currency counters, point of sales, and then card readers like barcodes, smart card readers. In the tolls you may see smart card readers and all. They will be the embedded systems now. These are all the different embedded system applications. You can also list out more. These are just 10 to 11 applications here we have mentioned. Then we need to understand what is the purpose of embedded system. What is the main purpose here? We will be collecting the data, we will be storing the data, and we will be representing the data. That is the main purpose of embedded system. And we do some data communication there. We may do some data signal processing as well, and we do monitoring the data and controlling the data, and we will be do some application specific user interface out of that. So this is the main purpose of any embedded system is. Suppose if we take a automatic automatic toll collecting system. So we will be collecting the data as a vehicle number. It will be detected by its own. It will do the communication between the car as well as the system what it is there, and it will do some processing, and it will monitor whether the amount is deducted or not, and it will do the controlling functionality of the toll gate. Then it will be having some interface. Like that we can easily understand the purpose of embedded system by taking any example. So here is the detailed answer for that. You can see data collection in the sense the purpose of data. What is the data we are going to collect? It will be analog signal or digital signal, and it may consisting of some sensor to collect that. All those comes under data collection, and we require some memory to store that, and how we are going to represent it. That is the first thing. The next thing is how do we communicate it. Suppose we will be having a wired system. There is a wired communication, wired connection. If we don't have a wired connection, we will be having Wi-Fi, we will be having GSM, Bluetooth or GPRS we will be using. And these are the things they will be used to communicate from one system to other system. That you can explain. Similarly, if you go to the wireless things, we will be having network, hub, router, switches, modems and all, right? This is part of the data communication process. Then we will be having data or signal processing. Once the sensor, suppose here is the sensor and here is the system. Once the sensor detects something, it will give the data to the system. This system will be, this communication will be a data communication. We call it as data communication. It can be wired or wireless. But in this system, what we are going to capture the sensor data, it will be having a processor. This will process the system. So this processor, it may convert from one form to other form. It may take audio into account. It may take image into account. If you take again a toll collecting system, it will detect the number plate and it will convert that into a code, right? That is what a data processing unit requires, right? Here some processors are involved. Then monitoring. Monitoring in the sense, we need to have a certain data monitoring system inside this system. It might be, suppose if you take an ECG machine, it will monitor the heartbeat. If you take a toll collecting system, it will monitor the number plate, numbers, right? And ECG are different electrodes will be there connecting to the patient body. So like this, you can take an example and explain how the monitoring will be done by using the sensors. Then controlling. Controlling will be, once the sensor give the data, we will be having some actuators. Actuators in the sense, again taking a toll controlling system, there will be a bar connected to the system. We can remove this bar which is holding or stopping the traffic once the sensor detect the number plate and the amount is detected. Actuator in the sense which one moves this bar. Sensor in the sense which will collect the number plate from the car, right? So that is what the control system is. And also you can give any of the example like AC, which contains a room temperature sensing element. Room temperature sensor will be there to collect the temperature, and it will be changing its temperature, right? That is the actuating system which will be setting up the to desired temperature. That is actuator. So then it will be having a user interface as well. So user interface will be some display unit. Once your car pass through the toll and the amount is deducted, it will show you the number plate and the car number, something like that, right? That is a user interface to make the user to understand what is going on. Then comes the very important topic here. So elements present in an embedded system, or a block diagram of an embedded system, we say. Here, what a embedded system consisting of? It will be consisting of a system core, right? It is consisting of some electrical hardware. That will be a system core. This system core can be a processor. This system core can be a microcontroller, microprocessor or microcontroller generally. So you can see here microprocessor or microcontroller. This can be FPGA, this can be ASIC, this can be DSP, or this can be SoC. FPGA in the sense it is field programmable gate array type. It can be programmable. ASIC in the sense it is one-time programmed application specific integrated circuit. DSP is digital signal processor. SoC is system on chip. And you know microprocessor and microcontroller. Any of these can be becomes a system core. Okay. Then there will be a memory attached to this. This memory can store the data. It can store a permanent firmware data, or it can store a temporary data to communicate as well. Then we may have some communication interfaces like USB. It can be USB, it can be Wi-Fi, like that. Okay. And some actuators. Actuators in the sense, as soon as a sensor detects the inputs, we may have sensors like push button switch. It can be a temperature sensor, it can be a humidity sensor, it can be a obstacle sensor, something like that. This will take the input, it give to the system, and depending on that, it will store some data, or it will learn from the firmware what we have, and it will give an action to the actuator. This will be a LED to indicate something. This can be a buzzer, this can be a audio unit as well. It can provide a sound output, like that. These are the actuators. It can be a 7-segment display to display some number as well. So those are actuators. This temperature sensor, humidity sensor, or a obstacle detection system, or a switch to turn on, turn off. These can be input ports of embedded system called as sensors. And there will be some supporting systems as well, like integrated systems and subsystems we have connected together with these to function it properly. To communicate with the external world, we require Wi-Fi. Suppose here is my sensor, there is no direct connection between them, so Wi-Fi is required to communicate. Or there might be a connection with a wire, so we require USB port over here to connect. So those are communication interfaces. And embedded firmware in the sense, to perform certain operation application specific, we have a software written into the memory, that is into the ROM. We have a RAM over here to store the temporary data and also to give back the data to the core. These are the elements. You can explain each and every elements like system core. This will be consisting of a microprocessor, and it can be a controller, it can be FPGA, it can be DSP, it can be application specific IC, or it can be SoC as well. You can explain them briefly. Similarly, embedded firmware. Embedded firmware is a software which is stored in a ROM. It can be a different types of ROM as well again. So like that, you can write 2-3 lines of explanation for embedded firmware, what it will do. Similarly, I/O devices. I/O devices in the sense it can be sensors. Through the sensors only, usually we will be taking the data. It can be a hard sensor device to like a push button, or it can be a switch like that, or it can be any temperature sensor kind of thing as well. And we'll be having output devices also. Sensors will be the input devices, and a buzzer can be a output device, or a audio output speaker can be a output device, or we can have LED as an output device. You need to explain these things as well. Then comes memory. Generally, we will be having two types of memories. One is RAM and ROM. RAM is used to store the data in a real time, that is working memory. ROM or EPROM are the different types of RAMs we are going to use to store the software in it, right? So these are the things correlated to memory, you can say. Then communication interfaces, as I said, it can be wired or wireless. So the protocols we will be using are I2C, SPI, UART, or a one-wire protocol, or parallel bus connecting as a wire, like that. So these are the things comes under communication interface. We will be studying these concepts at the end of this module. We will be understanding how I2C, SPI, UART works. Then there will be a wired media or wireless media as well. These are the things which will be support wired things. You can see USB, Ethernet and all when we connect devices to USB or to Ethernet port. Wireless in the sense Bluetooth or wireless LAN or infrared or GPRS we will be using. Then comes the other topic with respect to the embedded system components, that is the core of the embedded system. What this core consisting of? I said microprocessor, microcontroller or DSP, or it can be a programmable device. Microprocessor in the sense it can be 8085 or 8086. Nowadays we will be having later stage Pentium processors comes into picture. Now dual core comes into picture. Then i3, i5, i7 are the Intel processors we will be using, right? Those are the examples. In an embedded system, generally a less performance processor will be there, and i5, i7, i3 becomes general purpose. Then microcontrollers like 8051 and any other microcontrollers if you say. Then some DSPs to perform some critical operations. Then we may have programmable logic devices as well. This can be reprogrammed whenever we want. Then application specific ICs which are made only for that particular application. This IC will be programmed at the time of manufacturing itself that do particular application that can be used. Then commercial off-the-shelf components also can be used as a processor. So these are the core of the embedded systems. In this we need to understand what is a general purpose processor, we call it as GPP, and what is an application specific processor, that is ASIP. So here again a general purpose processor in the sense it will program, it will be get programmed and it will do the functionality. Whatever the programming we do, that accepts, that processor accepts. Application specific in the sense at the time of manufacturing only that processor will be dedicated to certain functionality, okay, that cannot be reprogrammed. Okay, so the application processors in the sense, suppose if we take an internet, so the network processing unit, router, all those are application specific. They can't be reprogrammed to do some other functionality. We can't do that. Some microcontrollers are going to be used as application specific as well. So let us move on. Then comes the microprocessor and microcontrollers. You know, microprocessors will be having CPU, will be having ALU, and we can connect memory to this as external device. But microcontroller, it will be having everything inside. CPU will be there, RAM also will be there, ROM, flash memory will be there, and timers, counters, everything will be there. But in the microprocessor, we can connect a CPU with ALU with different size of memories as external devices. There is a possibility. But in microcontroller, it will be strictly restricted to the particular microcontroller what we choose, which will be having certain memory, RAM, ROM, and dedicated ports like that. That is the major difference between microcontroller and microprocessor. Then DSPs will be faster general purpose, faster than microprocessors. It will be usually operate on 8-bit or 16-bit to 32-bit as well. And as I said, it is 2 to 3 times faster than general purpose MUPs. And we will be using DSPs to perform some complex operations on signals. Okay, so this can also be a core of the embedded system. Then we need to understand the differences between microprocessor and microcontroller. This is also a very important question. This question is repeatedly asked in exams as well. So basically you need to understand microprocessor and microcontroller in such a way that microcontroller is highly integrated chip. Okay, in a single microcontroller, we will be having CPU, we will be having RAM, we will be having general purpose registers as well, on chip ROM or a flash memory for programming storage, and also will be having timer, interrupt control unit, dedicated I/O ports. This will come in a package of single device, single IC. Okay, that is microcontroller. Microprocessor will be having CPU, which will be capable of performing different operations. Okay, and we are going to program them. But it will be not having internal ROM, it will be not having internal RAM as well. So timers and controls are externally we can connect. You can see here, this is the first difference. Second difference is, it is a dependent unit. But microcontroller is self-contained. Everything is contained inside. Okay. It doesn't require external interrupt controller, external timer, external UART. It is not required. Right? It is there inside. But in a microprocessor, this is just a CPU. Okay. It requires combination of chips. We need to use external timer. We need to use extra memory chips. We can use external interrupt controller as well to have that functionality. Here only CPU comes, but here with CPU, memory and interrupt control, dedicated I/O ports comes. That is what we need to understand the major difference. Then this microprocessor can be a general purpose design, but microcontroller is used for mostly application oriented or specific domain for specific application. Then it doesn't contain built-in I/O ports. I/O ports functionality need to be implemented within external programmable peripheral chips like 8255 we need to use externally. But in microcontroller, we will be having multiple built-in ports. It is there already. 8-bit or 32-bit or 16-bit ports will be available. So extra interfacing chips are not required here. Here it is required. Then triggered for both high-end market where performance is important. It can be targeted, means a microprocessor can be used whenever a performance is very important. But here microcontrollers are used in embedded market very much. It is not so performance oriented. Means less performance can be expected here. And then in power saving options, if you say, it is limited power saving. Why? Because all the external devices will be connecting to the microprocessor CPU. These are all external devices. So these may also consume some amount of time and also power. But in microcontroller, it will be a single device. It will be operating with the low power saving features as well. Includes a lot of power saving features. That is one difference between microprocessor and microcontroller topic. That is very important. Then comes the differences between RISC and CISC. This is a kind of processors and their operation. RISC in the sense reduced instruction set computing. Reduced instruction set. Here itself we can understand the difference, like the number of instruction set what we have is reduced, means less. Here complex instruction set computing means there are complex instructions are there in this kind of processors. So a controller or a processor, if you take, it will be based on the RISC type or it will be based on the CISC type. Okay. Here lesser number of instructions are there. Okay. Here greater number of instructions. Many instructions are there in this kind of architecture. In this kind of architecture, very less instructions. Okay. Then instruction pipelining and increased execution speed is there here. Here generally no instruction pipelining features are there in CISC. Then orthogonal instruction set, it means allows each instruction to operate on any register, use addressing modes, any addressing modes. But here in the CISC, all instructions are not allowed to operate on any register. Some instructions will be restricted to use particular registers. Okay, not all the registers are accessible to all the instructions it is. And use any addressing mode. And instruction specific, it is particular instruction to particular addressing mode or register, we can say. And RISC in the sense operations are performed on registers only. That is why it can access any registers at any time. Okay. And only memory applications are load and store applications. Here we will be having load instruction and a store instruction with respect to memory. Here the operations are performed on registers or memory dependent on the instruction. Here there are many instructions to do that. Here there are very less instructions. That's why memory operations in the sense we will be having only load and store here. But here we can do that memory load and store operations with any other operations with respect to the register is concerned and depending on the instruction is concerned. So here large number of registers are available. Here the registers, general purpose registers will be in limited number. Okay, means why? Because any general purpose register can be used with any instruction. But here large number of registers are there, right? To operate on any registers, allow each instruction to operate on any registers here. But here it is not allowed, right? It is not allowed. That's why it is a less number of registers. Here we will be having large number of registers. And in RISC, the programmer needs to write more code to execute the task, since instructions are simpler ones, very less complex instructions here, reduced instruction set computing, less number of instructions, right? That's why more code is required here. But instructions like macros are available in CISC. It will be requiring less number of coding effort, we can say, right? There is a major difference. Then here the instructions are in fixed length. Here variable length instructions are also available. Less silicon usage and pin count is required if you use RISC. In CISC, more silicon usage is required, means the silicon area is required more here, and complex instruction decoding as well. Then it is a Harvard architecture example, RISC, and it can be a Harvard or VonNeumann architecture as well with respect to CISC. So you can remember number of instructions and pipelining is supported or not supported. Then you can also with respect to the memory operations concerned, you can remember large number of register set are available, limited number is available, you can remember. And instructions, fixed and single instructions, length instructions, here variable length instructions are available. And also the usage of the silicon is less and more here. And with respect to the architecture is concerned, you can remember these 5 to 6 differences. These are enough to say the differences between RISC and CISC. Then what is Harvard and what is VonNeumann architectures with respect to the processor or controller concerned? So directly let us see the diagram, then we will be understanding. So there will be a CPU, always there will be a memory, and there will be an input and output ports like to connect sensor and actuators. What happens in the VonNeumann architecture of a processor, it has a single shared bus to connect all of them. Means only one bus is there, one wired communication is there. Through this wired communication, all the IO CPU memory has to get access. Means if CPU want to communicate with the memory, this will go in this fashion, right? If memory want to communicate with CPU, this will go in this fashion. It will be using this bus. At the time, CPU cannot communicate with the input-output bus. Why? Because this shared bus is already used to communicating memory and CPU. So that is how we need to understand this VonNeumann architecture and Harvard architecture. But if you see the Harvard architecture, it will be having dedicated bus. You can see CPU to memory will be having one bus, and data memory to CPU it will be having other bus. So CPU can at a time it can communicate to memory of program memory and data memory. Okay, but here shared bus is used, and suppose if you want to communicate with the program memory, it should be once, and after this communication is done, another communication need to be established. That is the major difference. So in Harvard architecture, you can see separate bus for instruction and data. But in VonNeumann architecture, we will be having single shared bus for instruction and data. Okay, instruction in the sense that is program memory. All the instructions are stored in ROM. But data in the sense there will be a data memory. It will be operate with a RAM usually, right? So there is separate bus for instruction and data. Here is shared bus for instruction and data. Then easy to pipeline here. So high performance can be achieved. Here low performance compared to Harvard architecture. It is comparatively costlier, it is cheaper, and no memory alignment problems comes here. Here some alignment problems will come. So allows self-modifying codes as well. Since data memory and program memory are stored physically in different locations, no chances of accidental corruption here of memory. Here data and program memory are stored physically in a same chip, chances of accidental corruption of memory. Then comes Little-endian and Big-endian processors. So a processor can understand the data in terms of Big-endian type, or it can understand in Little-endian type. There are two types. You can see here Little-endian and Big-endian diagrams. You will be understanding how the data will be stored. In Little-endian, this is your byte 0. This is byte 1. This is byte 2. This is byte 3. In Big-endian, at the top we will be having byte 3, byte 2, byte 1, byte 0. Okay, it is exactly reverse, right? So the base address plus 0 pointing to byte 0 here. Whatever the address you give, 2000. If you do plus 1, it will come to byte 1. So 2000 base address will be with respect to the first address or the base address. If you do plus 1, it will come over here. Suppose the base address in the Big-endian is 20,000, something like that. It will be pointing to the byte 3. Then if you increment, it will come down like this. Okay, that is how it is. So the difference between these two is the organization of data. Little-endian takes byte 3, then incremented to byte 2, byte 1 and byte 0 will be having incremented values in the storage. Little-endian operation will take byte 0 as the base, and as you increase it will go to byte 1, byte 2, byte 3. That is how it is. Then load and store operations and how the pipelining will happen in the processor. See, the general load and store operation with this example is concerned. So these are the registers. This is a register. This is also a register. This is also a register. Okay. So we will be having a load instruction here. R1, X, R2, Y, means X will be stored into R1, Y will be stored into R2, and we are adding R1, R2 and storing it in R3 like that. So we will be having these steps. So instruction pipelining, in the sense, we need to understand fetch, decode and execute. Okay, those are the three steps we need to understand. So directly we can refer to this diagram, a single stage pipelining concept. So we will be having clock pulses, means everything in the system will operate with respect to time using these clocks. Okay. So what we will be doing in this clock cycle 1, what we will be doing in this clock cycle 2, what we will be doing in this clock cycle 3. If you want to fetch, decode and execute, it will fetch here, it will decode here, it will execute here. It takes 3 cycles. Suppose if it is a pipeline one, while after fetching the data, while decoding, it will fetch the next instruction as well, right? While it is executing, it is already decoding the next instruction. Similarly, while fetching, decoding and executing the first instruction, here the fetching of the second, decoding of second happens. At the time, fetching of the third may happen. This is what the pipelining concept is. Okay. So there is a program counter that will hold the address of the next instruction, which is fetching or which is decoding, like that. So if the fetch instruction it will be having, means it is fetching the instruction and it will giving to the decode stage. By that time it is already fetching the next instruction. So program counter will be having that. You can see here in the machine cycle 1, or you can just treat it as a first clock pulse. Program counter will be having a fetch instruction, right? This fetch. Here decoding is not shown, directly execution is shown. It means in the first clock cycle, in any clock cycle, if the program counter is having a fetch instruction, means PC minus 1 is already in a execution stage, means the previous instruction is already in a execution stage. Similarly, the next clock cycle, it will already fetching the next instruction, PC plus 1, and executing the current fetched one. This will be executed here. So you can see here, this PC minus 1 is executed, already done. So PC plus 1, what is fetched, it is executing in the next stage. So while fetching PC plus 1, it is already executing the previous one. This will be called as pipelining. Okay. So in the next stage, it will be fetching the next instruction and also executing the previous instruction. So fetching this particular instruction will happen in this clock cycle. At the time, the previous clock cycle data is executing over here, right? That is what it is. That will be called as pipelining. You can go through this instruction pipelining steps for more information. Here is that example. So load R1, X, this will be a first instruction. Program counter will be pointing to this. And while executing this, already program counter moving to this, right? While executing this, program counter already moved to this. That is how it works. Then programmable logic devices. A device can be one-time programmable, or it can be multiple time programmable. Again and again we can program it. So we will be having a concept of programmable logic devices where we can reprogram it. Okay. So logic devices provide specific functions including device-to-device interfacing, data communication, signal processing, data display, timing control operation, like that. So there are two types here. One is fixed logic types or logic devices, another one is programmable. Okay, it means let us assume it as a chip. This chip can be act as a processor or anything. We can program it once, that we call it as fixed time programmable. Another chip, we can erase it and program the software again, that will be called as programmable. So programmable logic devices, in the sense, it will offer wide range of logic capacity, features, speed, voltage characteristics as well. So it can be reconfigurable any number of functions at a time. Okay, these devices are PLDs. Designers can use inexpensive software tools, quickly develop, simulate and test their logic on PLD. Why programmable logic devices are used means, this consists of some logic devices. When we program it, the internal connection is going to happen and it will perform some operation. Then the next program comes into existence, it will be removed in the sense, it will come back to the unconnected fashion. So there will be a logic structures inside, so they become unconnected. Something like let's say we'll be having 10 multiplexers inside, it will be having 2 adders. Those can be used depending on the program what we do, right? And these PLDs are rewritable memory technology. Devices can be reprogrammed and change the design. We can change the design and we can check how it will work, right? That is how the PLDs functions. Then comes the other type of PLDs, that is CPLD, complex programmable logic design, and FPGA, that is field programmable gate array. CPLD in the sense, complex programmable logic device. Similarly as PLDs, here this programming is a bit complex, something like that you can understand easily. Okay, so there are some specific gates over here in CPLD. Those number of gates can be programmed. Okay, so there are some less count over here in CPLD. FPGA will be having more number of cells. I said number of logic devices here inside, right, in a PLD. So there are high capacity in FPGA, there are less capacity in CPLD. So field programmable gate array, it means in the field, wherever we use that chip, we can program it. That is FPGA. Complex programmable logic device is also a type of FPGA, where the number of cells available for us to program is less. For small applications, we will be using CPLD. For bigger applications, we will be using FPGA. Okay. So you can see here FPGAs offer high amount of logic density, more features and high performance. CPLDs will be having small number of amounts of logic. You can see it can be containing 10,000 gates. Okay, and FPGAs can be containing more than that. So advanced FPGA devices offer built-in hardware processors. It will be consisting of a processor inside, and also it will be having memory, clock management system like PLLs. All those are there inside a FPGA. Okay, it will be doing data processing and storage as well as some telecommunication DSP applications as well. But CPLD offer very predictable timing characteristics, less critical timing controls like that. Okay, so the examples are Xilinx School Runner series, require low amounts of power and very inexpensive. So battery operated, cost sensitive. So CPLDs are very small FPGAs, we can say. Then come application specific integrated circuits. These are one-time programmable. At the time of manufacturing only, these ICs are programmed to do some certain functionality. You may see some ICs in your lab. It can be a NAND gate IC. This will do only NAND gate functionality. It can be a IC do addition, means adder IC. It will do only that. There will be another IC which will be operating as an it can be any amplifier. It will do only that performance. It will do only such application. Then we call it as application specific integrated circuit. It will do unique operation or specific operation. We can't reprogram it. We cannot do the reprogramming. So ASIC integrates several functions into single chip. Okay, that reduces the system development cost. And most ASICs are proprietary products. Means particular company will do that, and it will hold its all the proprietary information. Means that is restricted to that particular company, and it will be used in smaller systems with high capability, and ASICs are prefabricated. It means before the fabrication itself, that functionalities are defined, and then we will be using it in the requirement as it comes, right? So some companies will do ASICs for a particular customer. If particular customer require the device, something like that, so for the particular customer, the application specific IC will be done. So it is not refundable once it is done. So that's why non-recurring cost will be there. So the manufacturing of ASIC will take much complex process, since it is one-time programmable. If something goes wrong, we can't reprogram it and correct it. That's why the more charges, and we call it as non-recurring engineering charges, will be applicable, right? Then comes commercial off-the-shelf components. We call it as COTS. So which is like a off-the-shelf component, in the sense we will be having them as a application. We can use it when it requires. Like you can see some examples like COTS hardware units are remote control toy car unit that can be used whenever a toy car control system is required, including RF circuitry part. So that will be dedicatedly made for a toy car, right? It will perform high performance, high frequency microwave electronics devices, high bandwidth analog digital to converters. So these are the devices which will be called as commercial off-the-shelf components. Okay. So this is all about the different types of PLDs and the core devices what we have in embedded system. These all can be used. Then comes the memory. Memory is also an integral part of the embedded system we saw, right? After the core, we will be having memory. So there are two major kind of memories. One is ROM, another one is RAM, right? So this will be always data memory. This becomes a program memory or instruction memory, correct? So now, to have a program inside, we go for ROMs. Okay, random read-only memory. Okay, it stores the program instructions. Whatever the program you write as a firmware code in embedded system, that will go inside ROM and it will sit, right? So there are different types of ROMs. It can be a flash memory, it can be NVRAM, it can be PROM, it can be MROM, it can be EPROM and EEPROM. We need to understand what are these, what are the different types of ROMs available and how they will be storing the program. So remember, ROM can be programmable, means there are some ROMs which are static, some things are dynamic, means we can reprogram it. Let us understand. First one is MROM, that is masked ROM. Masked ROM, in the sense, this is read-only memory type. It is one-time programmable memory. Okay, it uses hardwired technology to store the data. Once it is stored, we can't reprogram it. Okay, so in the factory, while manufacturing itself, this ROM is programmed to do a particular function. All the instructions are stored there itself, right? So that will be called as masked ROM. It is masked. Okay. So the primary advantages of this masked ROM is low cost for high volume production. Once we can program it and we can do a high volume production. Okay. And different mechanisms used for masking the process, like creating of an enhancement or depletion mode transistor through channel implant, means this is a technology where we will be using the transistors while creating the MROMs. Some enhancement or depletion mode transistors are created, and by creating the memory cell, either using a standard transistor or with a high threshold transistor like that, and they will be used with a supply voltage to turn on the transistor above the normal ROM IC operating voltage, ensures that transistor is always off and memory cell stores logic 0, and when it is on, it will store logic 1 like that. Okay, so what is the limitation of these MROM? So with MROM based firmware storage is inability to modify the things. That's why it is hardwired. It is a factory made, factory programmed, correct? It is factory programmed. We can't change it. That is what the limitation is. Since MROM is permanent bit storage, so not possible to alter it. This is the major thing we need to understand with respect to masked ROMs. So with this knowledge, we can understand programmable ROM. We call it as PROM, or also call it as OTP. So PROM or OTP has nichrome or polysilicon wires arranged in a matrix. So like a polysilicon wires which are connected to transistors are arranged in a matrix like this. These wires can be functionally viewed as fuses. If we connect them or we can break them to make the connection or to break the connection like that. So then by doing that we can program them. Remember, there is a polysilicon wires arranged in a matrix format. We can do a programming by connecting and breaking. You can see here it is programmed by PROM programmer, okay, which selectively burn the fuses. Burn the fuses in the sense it is connected, we can burn it and make it as open connection, right? So whatever the bit it is required to store, it can be achieved, which are not, so fuses are not blown or burnt, represents logic 1. If you want to break the connection, it will be logic 0. That is what it is. So the default stage is logic 1. So OTP is widely used in commercial production of embedded system whose prototype versions are proven and code is finalized. Okay, low cost solution for commercial application is it is a low cost solution, and OTPs cannot be reprogrammed, but PROM can be programmable. So this is what programmable ROM is. Then we have, this is one-time programmable, let's say. This is one-time programmable. We will be having erasable programmable read-only memory. That will be called as EPROM. E indicating erasable. We can erase it and program it again. So erasable programmable ROM gives flexibility to reprogram the same chip. If it is once programmed, again we can reprogram it, right? So EPROM stores the bit information by changing the floating gate of the FET. Here FET is used. So please try to remember this. Here some blown or burning mechanism used with a polysilicon wire like a matrix structure. So in the masked ROM, we will be using a transistor, standard transistors, which is turn on or turn off with a high threshold value, or by giving the supply voltage 0 or 1 like that. And polysilicon matrix in programmable ROMs. Erasable programmable means we will be having floating gate FET concept, okay, and it will contain a quartz crystal window for erasing the stored information. So these are the process of how the programming and the reprogramming is done, how we are going to erase it. Erase it means by using a quartz crystal window is there for erasing the stored information. If the window is exposed to UV rays, then for a fixed duration entire memory is erased, okay. By blowing the UV rays into the chip, we can erase it, right, like that, okay. Then comes electrically erasable programmable read-only RAM. So electrically programmable VISA, we used quartz crystal as well as UV rays to erase. Electrically also we can erase the things, that is electrically erasable. You can see which gives flexibility reprogramming again. How we will be doing means it can be erased and reprogrammed within the circuit, okay. Electrical signals are there, register level or byte level. We can use them for alteration, right. So these chips include chip erase mode. There will be a mode chip erase. We can set it in the register, okay. Then we can easily erase the things and we can reprogram it. That is electrically erasable. Then comes the flash memory. This flash memory is also a variation of EPROM technology where it can be reprogrammed, and high capacity standard ROMs are flash memories, okay. So here there are different banks or blocks, or what we call it as pages, okay. It is arranged something like this, one above the other one, or it will be like different pages of memories, okay. It stores like an array in the sense, as we know, it will be having locations and rows and column wise it will store the data, okay. So the recent technologies where they will be using flash memory itself, okay. This is also an electrically programmable, and we can do reprogramming page level. We can do this particular page programmable, this programmable separately, okay. That is what the different types of random access read-only memories, okay. Then we need to understand RAMs, right, random access memory, okay. These random access memory RAMs is a data memory. Means whenever the operation is going on, the process is going on, to transfer the data we will be using RAMs. Okay, this is volatile in the sense as soon as the power is turned off, the contents in the RAM will be destroyed. Again, we need to program it or not program it. It will be come to useful only when the power is on. So RAM is direct access memory, meaning we can access the desired memory location directly without need of any traversing through the entire memory locations. Okay, so there are three types: SRAM, DRAM and NVRAM. What is SRAM? SRAM is static RAM. Okay, it forms it stores the values in terms of voltage. Okay, using flip-flops we have designed it. So the typical implementation of SRAM is with each and every bits which will be stored. A single bit storage requires 6 transistors. You can see here, this is the arrangement of the transistors. So this constitutes one inverter. This constitutes another inverter. We can say like that. So you can see here inverter 1 and inverter 2, which are connected back to back. Here is the write control, means whenever we provide this signal is equal to 1, data can be written and we can read the data from here, right? This static RAM is a 6T arrangement, or 6 transistors are required here to store 1 bit of information. Okay, and here you can also go through this to understand how the memory operation is. So just to recall, suppose if we have a data 1 here and we will be providing the write control bit as 1, this is bit line. Okay, and whatever the data we provide will go here and it will go to this inverter. This inverter invert that value to 0. Again it will give back to this, it will invert to 1. So this function continuously happen. Whenever we read the data through read control is equal to 1, we will be getting the inverted data over here. We need to invert it and get it as it is. This is how the system works here. Okay, write control and read control. Then comes dynamic RAM. Dynamic RAM in the sense, here the data will be stored in terms of charge. Right, charge in the sense we will be having a capacitor. Single transistor, one transistor and one capacitor is required here to store the data. This is called dynamic RAM. But here the thing is that this dynamic RAM requires refreshing. Means again and again we need to provide the data to store it here. Why? Because this capacitor leaked away the charge. Okay, the charge is leaked away. But here, because of the arrangement in such a way that one inverter here, another inverter here, these inverters getting the data again and again. 0 will come as 1 here, this one will be again 0, 0 will be changed to 1. So the voltage levels are maintained. Suppose 1 will be treated as 5 volts and 0 will be treated as 0 volts. This value get updated whenever we pass through an inverter. Okay, so the charge will be stored over here for a longer duration. But in the dynamic RAM, the data stored in the capacitor, this capacitor leaks in the sense it will store for a certain amount of time. As time gradually increases, the data stored, suppose if it is 5 volts, after some time it will become 4.5 volts. After some time it will become 3.5 volts. It will keep on reducing. So what we need to do, again and again we need to write the capacitor to store the value. So we call it as refreshing. We need to refresh the data. That is what the major difference between SRAM and DRAM. You can see it made up of 6 transistors. Here it made up of a single transistor and a capacitor. And it doesn't require refreshing, it requires refreshing. So this SRAM cell is used for low capacity, less dense, and DRAM is used for high capacity. Means higher end memory systems are using dynamic RAM. Okay, and it is most expensive. It is less expensive because less number of transistors and a capacitor here. Here 1 bit storage requires 6 transistors. But it is fast in operation. As soon as we take out the data, it gives correctly. But it is slow in operation due to refresh requirements. As soon as you request the read, we may require a refresh time as well. That's fine. It requires at least 60 nanoseconds access time. Write operation is faster than read operation here. Then comes NVRAM. NVRAM in the sense it is again a read access memory with battery backup. Okay, it contains a static RAM based memory. Okay, a minute battery providing supply to the memory in the absence of external power supply. Remember, these RAMs, whatever we say, are storing the data until we have a power. we are connecting with the power supply. If the power supply is gone, the memory will be vanished. That's why non-volatile RAM, in the sense it will be having some battery backup, that is NVRAM. So usually the RAMs are volatile, means it will lose the data. Non-volatile in the sense it will be having a battery backup for a minute, and it will store that even if the power is gone, and it will come back within the 1 minute or whatever the time duration, it can keep the data as it is. So since NVRAM is used for non-volatile storage, storage of results of some operations, setting up some flags, so those things need to be protected. That's why we can use some battery in that, right? So the lifespan is around 10 years. This is the device. Maxim or Dallas is an example for 32 KB NVRAM. Then we have sensors and actuators. Okay, so any embedded system, suppose this is a microcontroller or microprocessor, the input device will be a sensor and output device will be an actuator. Okay, input device becomes sensor and output device is an actuator. So sensor is a transducer device, means it will convert one energy from one form to other form. Means suppose if you take a temperature sensor, it will convert the temperature physical quantity into electrical quantity and it give it to the controller. So one form of energy will be converted into other form in sensor, also in actuator. In actuator also electrical form of energy is converted into some mechanical form or some movable form or some display kind of devices, displays, like that. So those two are transducers. Sensors are also a transducers, and also actuators are also transducers. It will be called as an input transducer, it will be called as an output transducer. It will be usually a mechanical or electrical unit, and sensors can be any mechanical unit as well, and also some electrical units also there. So very best example for an actuator is LED. Okay, light emitting diode. Why we use LEDs means to indicate something, right? After the processing in embedded system is done, we need to indicate something as an output. We will be using LEDs. LED in the sense light emitting diode. So this is a simple diode like this. Okay, whenever we provide an input, other than this dissipating the heat, it will produce a light in form of light. Okay, so it can be used as an indicator. You may get a question to explain LED. The first thing is it is light emitting diode. Diode in the sense it will be consisting of any diode. It will be consisting of two ends. One is a anode, another one is cathode, right? When we connect it to a positive terminal of the supply and cathode connected to the negative terminal of the supply, diode turns on, right? Similarly here, when we connect this to the P, this to negative, this diode turns on and light up. So there are two types of LEDs now. Okay, the first type is anode of LED is connected to port pin. Anode connected to port pin means this is a microcontroller. Microcontroller output pin is a port that is controlled the functionality of LED. In this case, what happens? Anode of the LED connected to port means anode is positive, cathode is negative. This negative terminal is already connected with the ground. Okay, it is connected to ground. Whenever we provide logic 1, this LED glows. Okay, cathode is connected to ground and anode of the LED connected to port pin. Port pin provides logic 1, LED forward biased and emits light. When port pin gives 0, LED is off. It means source current will be 0. Current sourcing in the sense will be providing the current to the LED, current sourcing, right? This is a general kind of thing. When we give 0, LED is off. When we give 1, LED will be on. The second thing is current sinking. Here this end is anode, this end is cathode, or we can write it as K. This end is positive, this end is negative. So here what happens? Anode is already connected with some positive supply. Okay, we are waiting for this port of the controller to go low. If it is 0, then forward biased is happening. Okay, so this will be called as current sinking. This device or this port will be taking the current in this way, but in the current sourcing manner, diode anode will take the current and give it to ground, right? This is current sourcing. Syncing in the sense we will be controlling the LED functionality through the reverse manner. If we provide 0 through the port, LED will be on. If we provide 1 from the port, LED will be off. Okay, you can see here diode turns on when port pin is 0 and port pin sinks the current, takes the current. Here port pin gives the current, and brightness of the LED can be increased by increasing the to the required level by providing the negative voltage from the port that can be controlled. That is what LED is. Okay, then comes the 7-segment display. By using 7 LEDs, okay, we can have a 7-segment display to display the numbers or any alphabet. Okay, so here you can see 1, 2, 3, 4, 5, 6, 7, 8 LEDs are there. 7 LEDs for representing the light, and this dot sometimes we need to display 7.4. This dot is used to display the decimal point. Okay, generally for any alphabet or a number, if you want to display, we require 7 LEDs. You can see this is 1, 2, 3, 4, 5, 6, 7. 7 LEDs are required to display any number. That's why it will be called as 7-segment display. It will be, but it will be containing 8. Why? Because to display the dot. Okay. So now, similarly in the previous LED, how we understood the current sinking and current sourcing, here also the same functionality works. Means, if you can control the LED turn on, turn off using cathode or using anode, there are two different types comes. One is common anode, another one is common cathode. Common anode in the sense what? In the diode, this is anode, means it requires a positive supply to connect. In cathode, it requires negative supply to connect. Means whenever we have a common anode functionality type, anode is already connected to supply. Okay, so we provide 0 from the cathode to turn on, right? If you want to display 2, it will display like this, right? This is 2 displaying 2 in a 7-segment display. So in this, you can see the labeling here. LED A, LED B, LED C is off. This is LED D, LED E and LED G. These things should get 0 value to represent value 2. Okay, that is common anode. Common anode configuration, all the LEDs of anode will be connected to VCC already. We need to provide 0 to turn this on. Okay. Similarly, common cathode is there. In common cathode terminal should be always connected to ground. It is already connected. We need to provide 1 from the anodes to program them. Suppose if we want to display A, we need to provide 1 in the common cathode method. In the common anode method, we need to provide 0. That is how it is. Okay, there are two types. So you can see, suppose if you want to display a number 0, here the code is 03 in hexadecimal. Why it is 03 means 0 in the sense 0, 0, 0, 0. 3 in the sense it is 0, 0, 1, 1. Okay, there are 8 values, correct? So to display 0, all the LEDs should be on, means all these external LEDs should be on. This should be off, right? That's why here it is 1. And this dot will be the last value. This should be 1. This is a common anode mechanism. Common anode in the sense, when we are providing 0, that particular LED, this is A, this is B, C, D, E, F, G and a dot. Okay, we are not supposed to display dot, we are not supposed to display G. That's why these are provided with 1. All zeros will turn on these lights. Okay, this is common anode mechanism. LED can be common anode or common cathode. Here we are showing common anode method. And with the microcontroller, when we are going to access that, here is the 7-segment display and the ports are connected in this fashion. There are 8 ports need to be connected. This is for A, this is for B, this is for C, this is for D, E, F, G and a dot. Okay. So whenever, if this is a common cathode method, common cathode in the sense we need to provide 1 from A so that this will be displayed. Similarly, if it is cathode means from this port we need to provide 0 so that it will be displayed like that. Okay. So 8051 microcontroller has ports. Those ports will be connected to the 8 LEDs. Okay. those 8 LEDs will be getting the values and it will display the number. Then comes the output device called optocoupler. Optocoupler in the sense it is a LED and a photo detector, we can say. So you can see here photo transmitter device. Okay. Then let's see optocoupler. Photo transmitter in the sense whenever LED is turned on, there is another device to detect that and it will pass on the signal. Okay, something like that. Photo transistor. So photo transistor will be a combination of LED and a transistor. So this device will detect the LED light and it will generate some output signal. And by using this, you can see there is a optocoupler device. We call it as an optocoupler. Okay, how we can use it means, so there is an intruder detection system. So there is a door over here. Okay, so we will be connecting an LED over here. It will be continuously glowing. Here is a transistor which will be keep on detecting it. Okay, it will be receiving it continuously. Some person come over here, this LED will be break down, right? Then a zero signal will be passed from here. So these kind of optocouplers can be used to detect something which is blocking the region of LED as well as a detecting system. Then it is connected to a microcontroller as well. Suppose if the data is broken, it will take some action from the port, and again the same kind of optocoupler is used here to transmit the signal. So here continuous high voltage, so you can see in the electronic circuits optocoupler is used for suppressing the interface in the data communication. You can separate the interface here. Means circuit isolation, high voltage separation, simultaneous separation. So these things can be done using optocoupler. Means here we will be having opto in the sense light, and this coupler will be using some circuit. So this optocoupler containing a LED and a circuit, right? This is also an transducer. Then comes relay. This relays will be having a electromechanical circuitry or device. It acts as a dynamic path selector for signals. You can see here there will be a switch here and there will be a coil here. When we are energizing this coil, it will be called as single pole single through normally open relay. Whenever this coil is energized, this switch will be closed. Otherwise, when there is no voltage to the coil, this switch will be generally open. That is a simple thing. Okay. Similarly, single pole single through normally closed. Normally the thing is a switch is closed. Whenever we energize this coil through some value, this becomes open. And we will be having single pole and double through as well. Whenever we are going to energize this coil, it will be connected to the second pole, otherwise it will be connected to the first one. So there are three arrangements here, you can easily understand. So single pole single through in the sense there is a single switch. Single pole double through in the sense there is a two switch mechanism, right? Then we can also use it for any application like this. You can see there is a motor, there is always a AC connector over here, there is a supply. But whenever we turn on this switch, then only this motor will be turned on. This can be controlled by a microcontroller arrangement. There is a port pin here. So this port pin, suppose if we start providing logic 1, there is a resistor here to the gate of the transistor. So sorry, base of the transistor. Whenever this base gets an positive voltage, this transistor will be turned on. It means whatever the voltage we are going to provide it here will pass through the transistor and it will go to ground. Until we provide 1, this transistor will be act as an open circuit. If we provide 1 from the base, this becomes closed circuit. Then only the current flow through the coil and it will make the switch to turn on. Okay, it means the transistor will be turned on when logic 1 is provided from the port pin from the microcontroller. It turns on the relay coil energized. Otherwise, it will be in the normal closed operation. Okay, and motor will be turned on. This is a simple application of a relay which will be having single pole through. You can also use a double pole through here in place of this relay. Suppose a connection will be something like this. It is always connected. We will be having another pole. Whenever this relay is energized with the port pin, it will connect it to this. Otherwise, it is connected to this. Then comes the Piezo buzzer. There is an output device called buzzer. Buzzer will make a sound, or we'll be using for some operation, right? Means to indicate some indication, right? So this will be a piezoelectric device generating the audio indications. So the Piezo buzzer contains piezoelectric diaphragm, which produce audible sound when we are giving some external voltage to it. So buzzer can be used in the alarm. Okay, it will be a fire alarm or intruder detecting system. One thing is self-driving, another one is external driving. Self-driving in the sense, it will generate the sound at predefined, it will generate a predefined sound by applying the voltage. Okay. External driving in the sense, depending on the voltage, we can generate different tones. A tone can be varied by applying a variable pulse train through the piezoelectric buzzer. Generally, this piezoelectric buzzer will be consisting of a vibrating film. So depending on the voltage we provide, the vibration in this piezoelectric device changes. Depending on that, the different sounds will be produced. You can see one such example here. There is a port pin. When we provide one, the transistor will be closed circuited, and whatever the voltage we provide will be, it becomes a complete path over here, so that it will make some buzzer sound. So when this buzzer will be turned on means when we are providing logic 1 from the port. So that will make the transistor on and buzzer on. Then we have a next concept called push button switch. This is an input device. This push button is a basic input device of an embedded system, okay, to a microcontroller. You can see here, this is the arrangement of a push button switch. When we press this, this becomes closed switch. Okay, the switch will be closed. When it is pressed again, it will break the circuit. That is how it is designed. This is a mechanical device. When we press it, it will go and fix the connection. When we press it again, it will be released. Okay, it will break the connection. Just to make the connection and break the connection, we will be using a kind of button that will be called as push button switch. Okay, you can also use the push button switch like this, right? You can give the input to the microcontroller by providing this push button switch. When it is pressed, the circuit will be providing the one to the logic microcontroller. This will turn on the LED. If we release it, it will open and LED will be off, something like that. So then comes communication interface. Communication interface in the sense, these are required in the embedded system to connect them to the external world. Means if you want to connect any other device with the embedded system, we require some communication interface. It is like you will be having a mobile phone, okay, but you will be having a socket over here to connect the charger, right? You will be connecting the charger to an USB pin. This is your USB. So this USB becomes a communication interface. Similarly, some devices, means inside a embedded system also, we need some communication from memory to CPU. There will be a bus communication. In such cases also, on-board communication interfaces will be there, and these things will be off-board communication interfaces. So let us understand which are all those and how the communication will be happening in that communication interfaces. Generally, they will be having some protocols. They will follow some standard method for communication. So the very first thing is board level or device communication interfaces. Means they will be there on board, inside the board, we can say, on the board, PCB. So embedded system is a product combination of different types of components. Means chips are devices which will be arranged inside a chip. We will be placing on a chip like this. There are some interfaces like I2C, SPI, UART, one wire and parallel bus are the communication interfaces which will be there on board. Means from this device to this device we need to communicate, means I2C protocol will be used or some UART protocol will be used. So these things we need to understand. Okay. Then the second type is product level communication interfaces. Means product level communication interface in the sense for data transfer between the embedded system to other devices or modules. We call it as external communication interfaces. As I said, USB can be one thing, or infrared will be used, or Bluetooth will be used. Sometimes from the mobile to the PC, if you want to communicate, we will be using Bluetooth connection to the transfer of data. So that Bluetooth becomes a external communication interface, while I2C, SPI, UART are onboard communication interfaces. Okay, and also we'll be having, as I said, a USB. We'll be having Ethernet like LAN cables, parallel ports, CF2 slots, and all these are external communication interfaces. This can be wired or wireless as well. Bluetooth in the sense it is a wireless communication. USB in the sense it is a wired communication. Ethernet is an internet, means the cable, LAN cable, that can be a wired communication like that. So to understand I2C, you can see here I2C, it is also called as I2C. Okay, the concept of I2C bus was developed by Philips, okay, in 1980s. It will be having two buses. Remember, there are two signals we can say in I2C. Okay, I2C will be having two signals. Okay, and this is from point to point communication. We will be having one signal called SCL, that is clock. Another signal will be called as SDA, that is data. Here SCL is a clock signal that will transfer the data with respect to time like this. This SDA will be send the chunks of data in each and every clock cycle. Okay, so I2C bus can be a master device or slave device. Before that, you can see a serial clock and serial data. This is serial communication. One after the other data will be transmitting like this. And we'll be having a concept of master and slave. One device which will be sending the data will be a master. Other device which will be receiving the data will be slave. In between, we'll be having I2C communication, means we'll be having one line connected as a clock, other line which will be sending the data, right? So what happens? Master device is responsible for controlling the communication, means initiating the transaction. It's say I am writing into the data, it is reading the data. Everything will be controlled by the master. Slave will be just receiving the data. Like master is data transfer, sending data, generating necessary synchronizing pulses. But slave device wait for those commands from the master and respond depending on that. Okay. So master can be a transmitter or receiver, and slave can always say transmitter and receiver, but initiating the transaction will be from the master. Okay, then I2C supports multi-master communication also. Okay, multi-masters on the same bus. You can see here, this is the example where we will be having slave 1 and slave 2. We will be having only one master, that is microcontroller or processor. We will be having port pins of the controller. This pin can be a data line, this pin can be a clock line. You can see these two are connected to VCC, that is required to provide some voltage levels, and these two pins are connected to one slave, these two pins are connected to other slave. Okay, so depending on the data or depending on the address of this particular device, okay, I2C will be having some certain pattern to send the data. Depending on that, we will be choosing slave 1 or slave 2. It will be having a chip select or a chip select address. Depending on that, we will be selecting this device or this device. Okay, how the operation will be, let us see here. Master device pulls the SCL, pulls the clock line to high, means master will make this transaction first, this SCL to go high. Master device pull the data line low, data line will go low at this time. When SCL logic is high, it will indicate the start condition. When SCL, SDA is low, this is SDA low, and SCL is high, this will be indicating the start of transaction. Okay, this is indicating the start. Then master sends the address. I said there are address bits, 7-bit or 10-bit of the slave device. So through this line, through this data line, the address will flow, and whichever the address which is detected by the slave, that slave will be connected, and that slave communication will happen from the master depending on the slave device address. Okay, so clock pulses are generated from SCL line for synchronizing the bit reception by the slave as well, and MSB of the data is always transmitted first. Suppose if you want to send 1011, this is MSB, this will send first, and this will next, this will be next, this will be next. That is how the transfer will be. MSB data is transfer first. Okay, if it is high, it is a data 1. If it is low, that is 0. And also master sends read write bit. There will be a read write bit as well. Depending on the operation, bit value 1 means read operation, bit value 0 means write operation. And also slave can send the data as acknowledgement. Slave will send the data, master wait for that. So slave device will send that whose address is sent on the bus is correct, and also with the read write operation, right? Slave device connected to the bus comprises of address received with address assigned to them, right? So there are different addresses for this. This slave device can be having 0 to 100 addresses, and this will be having 101 to 200. So whenever the address comes as 50 through this line, so this will catch up and this slave will be active, and on that time this slave 2 will not be responding. That is how it goes. Okay, so that is how the communication is. The slave device with that address requested by the master responds by sending an acknowledgement bit from the slave also through the SDA line only. So this slave communication will happen to the master. So there is a I2C format as well. So first start bit will be there, then address will be there, then acknowledgement will be there, then data will be there, again acknowledgement will be there. The process goes on like this. First start bit will be sent, then address will be sent, then waiting for the acknowledgement, then data, then acknowledgement, like that. So depending on the acknowledgement what the masters receive back from the slave, the next communication will be forwarded from the master. Okay. So upon receiving the acknowledgement bit, master sent 8 bit of data, right? So now the address is sent and we get the acknowledgement bit. Now we will be sending the data, right? Write to device, right? If the operation is read operation, there will be a write read bit over here. After the start bit is say write or read operation bit will be there. Depending on this, next data will be sent or waiting for the data to receive from the slave. If it is a read operation, master wait for the acknowledgement bit upon transfer of the complete information for write operation as well as for the read operation, right? Then master terminates the transfer by pulling the SDA line high. SDA will go high continuously when the clock line SCL is logic high. This is stop operation. Start operation is that SCL will go high and SDA will go low. When SCL is high, SDA go low. This is start operation and this is stop operation. So here, this process you need to explain if they ask I2C. Okay, you can write at least 2 slave diagram. There will be address like this, address set 1, address set 2. Address set 1 will be corresponds to slave 1. By looking at the address only, the slave will understand this is related to my address, like that. So the communication in I2C will happen in 2 buses. That's why it is I2C. Then comes a onboard communication interface, another one, that is SPI. SPI in the sense it is serial peripheral interface. Even I2C is also a serial one. Here SPI is also a serial one. Okay. This is bidirectional full duplex, but I2C is only half duplex. Whenever master sends, slave has to wait. When slave sends, master has to wait. Now this is full duplex communication. What and all the signal lines present here? Here we will be having master out, slave in one line. Master in, slave out is other line. So in I2C what happens? Through SDA only master sends and slave sends. So one has to wait for the other turn. But here master out is one line, master in is other line. Master out in the sense that is slave in. Master will send the data to slave. Here slave will send the data to master. There are 2 separate lines. Also we'll be having a clock signal similarly as I2C, and we'll be having a slave select signal line as well. So that avoids the confusion between the slaves. So we say SPI is introduced by Motorola and it will be a multi-master and multi-slave system. Okay, you can see the diagram here. Similar diagram what we see in for I2C, but here there are 3 signals for communicating and 2 signals for selecting the slave. Okay, if SS1 and SS2 are properly chosen, whether this slave has to be selected or this slave has to be selected, depending on that the slave devices will be active. So master is responsible for generating this SCL clock. This is also a similar kind of clock what we seen, and this master will be selecting the required slave by asserting device slave select signal SS1 or SS2. Okay, When the slave select signal is low, you can see here, when the slave select signal is low, corresponding the slave device will be selected, asserting them, right? The data line MISO for all slaves, the data outline, that is master in slave out, of all the slave devices when not connected floats high impedance state. Means if this is master in slave out, if it is not connected, it will be in the Z state, high impedance state. Okay. So since it is a serial data communication, it is fully configurable to dual state. It means master in slave out means this will be an output signal from, master in slave out means it is an master to input signal. Master out slave in means this is an output signal from the master. Similarly, from the slave perspective, master out slave in means the data will come out, come like this: master output, slave input. Okay, master input, slave output means slave will give the data through this signal, right? And we need to understand the working here. Okay, so it contain some registers. SPI devices or the slaves contain a set of registers holding the configurations and the addresses corresponding to that. Okay, and there will be baud rate selection will be there, clock signal control will be there. So how the SPI works means we'll be working in the principle of the shift register. Master and slave device can control this special shift register for data to transmit or receive. Okay, this size of that shift register bits may be 8-bit or shift register is a 16-bit, dependent on the device, a kind of device what we use. Generally it will be in a multiple of 8 cross. Okay, it will be 8 or 16 or 32 or 64, something like that. And during the transmission from master to slave, data in the master's shift register is shifted to this pin, master out, slave in pin. It enters to the shift register of the slave device, that is MOSI pin of the slave. At the same time, shifted data out from the slave device, shift enters to the shift register of the MISO pin. Means we will be having MISO as well as MOSI. This is master output. Master will send the data to the shift register of the master. It will be received by the shift register of the slave device and through the master output slave in of the slave, right? This is slave device. So shift register is there here as well, here as well. This is about SPI. Okay, you may get a question on SPI and I2C as well in exam. You need to explain how that work and what are all the signal lines present, and you need to write this diagram. This diagram is very important to fetch the marks. Then we have external communication interfaces. So far we have seen onboard communication interfaces. This I2C is and SPI are onboard. On the board, if the different IC need to be communicated, then they will use I2C or SPI. Off the board in the sense external device, infrared. Infrared is a wireless communication mechanism. It is also a serial. It is half duplex in the sense this device and this device. It can send the data. It should wait for the data to be completed. Then this side can send the data. This is like a walkie-talkie. This person can start first and this person can listen. After he completes it, this person can talk, this person can receive. This is half duplex. Full duplex in the sense at a time, both can communicate. Infrared uses a wireless technology. It uses a technique makes infrared waves to transmit as electromagnetic spectrum, and it is point to multi-point communication as well. Okay, means one person can talk and multiple person can listen like that. The range will be 10 centimeter to 1 meter. Within 1 meter we can have a communication, and infrared supports 9600 bit per second, that is 16 Mbps speed. Okay, this is classified into serial infrared, serial IR, medium IR, fast IR and very fast IR and ultra fast IR as well. So this will be depending on the bit rate or the Mbps what we say, right? And this is what the basic idea is. So serial interface supports ranging from 9600 bps to 115.2 kbps as well. MIR supports the data rates from Mbps in the range of Mbps. This is in the range of kbps. Okay, FIR, that is fast, will support up to 4 Mbps. VIR, that is very fast, support up to 16 Mbps. and UFIR, that is ultra fast, will support up to 100 Mbps. So then comes the Bluetooth. Bluetooth is also a external communication interface, and it is a wireless technology. It is also a short range. Remember, in infrared will be used only in up to 1 meter, 10 centimeter to 1 meter. Bluetooth will be having some higher distance. You can see 30 feet distance. It will be go up to 1 Mbps range. It will uses 2.4 gigahertz of the radio frequency. That is the operating frequency of the Bluetooth. Okay, 2.4 gigahertz, right? And then Bluetooth communication happens in different layers. Layered communication will be there. Physical link part is there and a protocol part is there. Okay, physical link in the sense it will be data transmission between the devices. Okay, device level, application level we say. Protocol level in the sense it will be having a encryption decryption mechanism inside, right? So physical link works on the wireless principle, making RF waves to communicate. Okay, and Bluetooth enabled devices especially contain Bluetooth wireless radio. It should have this wireless radio for transmission and reception. And Bluetooth rules are whatever the protocol contains will be having Bluetooth protocols stack. The Bluetooth communication IC holds the stack. Means there will be a Bluetooth IC inside that will manage just the communication. So this will allow 48-bit unique identification number for the devices. So multiple devices, when it is trying to connect, it will be having unique identification number with 48-bit. Okay, so it based on the packet transfer. There will be a packet information transmitted at a time. And it supports point-to-point and point-to-multi-point as well. Means sender can be single and receiver can be multiple. That is what point-to-point. Point-to-point is single to single. Point-to-multi-point means multiple receivers can be there. And Bluetooth can function either as a master or slave. This can be a master or this can be a slave as well. Now this can be slave or this can be master, like that. Okay. And network formed one Bluetooth device as a master and more than devices as a slave. So as I said, these are slaves and single will be a master. That is Bluetooth. The range will be up to 30 feet. Okay, and 1 Mbps speed. Then comes Wi-Fi. Wi-Fi in the sense it is a wireless fidelity, means wireless internet we can say. This will be having a standard IEEE 802.11. Okay, it is a popular wireless communication technique. This requires a network communication, especially for with respect to IP is concerned. It will be work on IP communication, means every device will be having a IP set. Then depending on that, it will communicate. So this requires a Wi-Fi router and Wi-Fi access point to manage the communication. Okay, and here the router is responsible for restricting the access to the network. This router will be having certain IP address supporting. So it will access the IP address to the device on the network, routing the data packets to that particular device or the IP. And Wi-Fi enabled devices contains wireless adapter will be there for transmitting and receiving the data. And the operation speed is 2.4 gigahertz to 5 gigahertz of radio spectrum. And as we seen in the Bluetooth, it will be also 2.4 gigahertz. And here Wi-Fi network identified as with a SSID. There will be a service set identification number which can connect to the network by selecting this number of the other device, providing the password or credentials, what we say. And also it will allow different security mechanisms as well. Authentication and data transfer will be encrypted and decrypted at the endpoint. Okay, and it will be having wireless equivalency protocol WEP and wireless protected access WPA. These are the protocol standards which will be used in the communication of the Wi-Fi communication. Okay. Then this is a simple diagram. There will be a router and device 1, 2, 3 connected. That can be a mobile or any other devices. Then also we will be having another external communication interface, that is ZigBee. ZigBee is low power, low cost wireless network communication protocol. The standard IEEE standard is this. Okay, IEEE 802.15.4-2006 is the standard. This is a low power protocol actually. Low power, low data rate as well, and for secure applications we can use this in wireless personal network. ZigBee supports robust mesh kind of network with multiple nodes connected together, and this will be again uses 2.4 gigahertz range, okay, and 902 to 928 megahertz and 868 to 868.6 megahertz. This is what the spectrum is. And 100 meters, up to 100 meters, this ZigBee can be used. Bluetooth will support up to 30 meters, right? And the data rate here it supports in 20 to 250 kbps. ZigBee is generally used in home or industrial automation, medical, patient tracking, home security system, logistics and asset tracking. So there will be active RFIDs, so where the ZigBee will be useful. And these are some applications you can list out. There are many applications which will be hold good home industrial automation or security systems like that. Then ZigBee terminology, which a ZigBee device falls under one of the following ZigBee device category. In the ZigBee terminology, ZigBee device falls under one of the ZigBee category. Which are those? ZigBee coordinator, or we call it as network coordinator. Other one is ZigBee router. Another one will be a ZigBee endpoint. Okay, you can see here. This will be a coordinator. Okay, this acts as a root of the network. This is the main part of the network. This is a root of the network. Okay, this will initiate the network and has capability to store the information of the network. ZC indicating ZigBee coordinator. And there will be a router as well. Similarly, as we seen in the Wi-Fi, there will be a router to connect the endpoints. This is responsible for transferring the information to the different endpoints. Then we will be having ZigBee device. This is a endpoint device. So these endpoint devices will get those information, whichever the coordinator or the router sends, right? Here this ZC can be connected to multiple ZRs. Means ZC is a coordinator or network coordinator. This can connect to multiple routers. Router can connect to multiple devices again, right? This is how the device organization is. Okay, so here in these things you need to remember the range of the radio spectrum and in which applications they will be used and what is the standard is, and if any diagram supporting that you need to write in exam. This is much required in the exam point of view. Okay, so that is all about the different topics in module 1, starting from embedded system definition to the external and onboard communication interfaces. So these are some recommended questions or important questions in this module. What is embedded system and mention applications can be asked. Explain the purpose of embedded system with an example can be asked. How embedded systems are classified. There are different methods of classification you need to write. Applications of embedded system with example can be asked. And there is a neat diagram of embedded system. This is very important. And course of the embedded system, different processors and how the controllers can be used and how they will be useful in embedded system. At least 2 in detail they have asked. And this difference between the things, general purpose embedded and general purpose computing and embedded system, MUP, MUC, RISC, CISC, Harvard, VonNeumann, Big-endian, Little-endian, SRAM, DRAM. These are very important. At least one question we can expect easily in exam. Okay, generally MUP, MUC and RISC, CISC, Harvard and VonNeumann, general computing to embedded system are repeatedly asked. Even in basic electronics we have seen these things. And then comparing the programming logic devices and ASICs and COTS can be asked, and the different types of programming logic devices, FPGA, CPLD can be the questions. Then what are the different types of memories used, RAM and ROM. And again in ROM there are programmable ROMs. In RAM again SRAM, DRAMs are there. You need to understand them. Explain role of each, where it will be used and how. Explain SRAM design and features with diagram. 60 cell you need to explain it here. And the arrangement of that with respect to the 2 inverters connected back to back need to be explained. Then optocoupler connecting LED and a transistor is the diagram you need to write and explain. Sequence of operations of I2C, there are some 10 to 11 points there. SCL, SDA, how they are going to be a start bit and stop bit and the data communication and how the acknowledgement will be. All those things need to be explained. And also write the diagram when they ask I2C and SPI. Okay. And also you need to write those points clearly, how the start bit is, end bit is, and what is the mechanism that will be used. And if you see SPI, master input, slave output, master output, slave input, and two select lines, all those things you need to explain it clearly. That's why you need to write a diagram there. Then comes infrared, Wi-Fi, ZigBee, Bluetooth can be asked for explaining them for 5 marks. That is also a very important question. So don't leave any question here. In exam, it can be like anything can become important here, but these differences are very important, and the diagram is very important, and what is embedded system and applications is important, and also the classification can be asked many times. Okay, so these are the very important concepts, and out of these two one can be asked. Okay, so this is all about the module 1. In the next lecture, let us see module 2 and let us cover them in one shot. Thank you.